Hello YouTube, my name is Neil and we're studying for the MCATs today. We're in the Organic Chemistry Review, Chapter 7, Aldehydes and Ketones, Part 2, Enolates. In the previous chapter, we took a look at a few key concepts and reactions of aldehydes and ketones. These molecules have highly predictable chemistry centered on their electrophilic positively charged carbonyl carbon and will be sure to show up on test day. In this chapter, we take a look at several more properties of aldehydes and ketones and focus on the reactivity of the alpha hydrogen of carbonyl containing compounds. The acidity of this alpha hydrogen allows many aldehydes and ketones to act as both electrophiles and nucleophiles. Sometimes they can even serve both function in the same reaction, but don't worry, we'll also review some tips about how to understand when and how aldehydes and ketones will react. General principles. In the previous chapter, we focused on how the electronegativity of the oxygen atom in a carbonyl pulls electrons away from the carbonyl carbon, making it partially positively charged. In this chapter, we take the electron withdrawing characteristics of oxygen one bond further, focusing on the alpha carbon in an aldehyde or ketone. Acidity of alpha hydrogens. An alpha carbon is adjacent to the carbonyl carbon, and the hydrogens connected to the alpha carbon are termed alpha hydrogens. Through induction, oxygen pulls some of the electron density out of these CH carbon-hydrogen bonds, weakening them. This makes it relatively easy to deprotonate the alpha carbon of an aldehyde or ketone. As shown in figure 7.1, the acidity of alpha hydrogens is augmented by resonance stabilization of the conjugate base. Specifically, when the alpha hydrogen is removed, the extra electrons that remain can resonate between the alpha carbon, the carbonyl carbon, and the carbonyl oxygen. This increases the stability of this enolate intermediate, described in the next section. Through this resonance, the negative charge can be distributed to the more electronegative oxygen atom. The electron withdrawing oxygen atom thereby helps stabilize the carbanion, a molecule with a negatively charged carbon atom. When in basic solutions, alpha hydrogens will easily deprotonate. And here we have a diagram of the deprotonation of an alpha carbon forming a carbanion. Let's draw this. You have the oxygen double bonded to a carbon, the carbonyl carbon. We have an R group on one side, and then we have the carbonyl carbon attached to the alpha carbon, which is also attached to an R group. And we have a hydrogen coming off the alpha carbon. That's the alpha hydrogen. Let's put in a little alpha for alpha. And then after, we have still got the R group on the right, but instead of the hydrogen on the alpha carbon, we have a lone pair of electrons, and that is our carbanion. Put a little negative charge on it. Let's draw some arrows like so. We also have this is in the presence of a base, OH, hydroxide, because that is what is going to attack the hydrogen and then the electrons go into that carbanion. The alpha hydrogens of ketones tend to be slightly less acidic than those of aldehydes due to the electron donating properties of the additional alkyl group in a ketone. This property is the same reason that alkyl groups help to stabilize carbocations, but in this case they destabilize the carbanion. So alkyl groups stabilize carbocations but destabilize carbanions. So let's write that down, that the pKa of aldehydes, or ketones I guess, ketones, aldehydes is less. And by pKa being less, we mean that aldehydes are more acidic, ketones are less acidic. Let's also write that alkyl groups stabilize carbocations but destabilize carbanions. All right. Steric hindrance. So I guess we could write down that this is about acidity. And this is steric hindrance. In reactions, aldehydes are slightly more reactive to nucleophiles than ketones. This is due in part to steric hindrance in the ketone, which arises from the additional alkyl group that ketones contain. When the nucleophile approaches the ketone or aldehyde, in order to react, the additional carbonyl groups on the ketone are in the way, more so than the single hydrogen of the aldehyde. This makes for a higher energy, more crowded intermediate step. Remember, higher energy intermediates mean that the reaction is less likely to proceed. Steric hindrance. Ketones are less reactive than aldehydes because of steric hindrance. Why are the alpha hydrogens of aldehydes and ketones acidic? Because the carbonyl oxygen is happy to take electrons. And so the hydrogen can leave as a positive ion. 2. Are the alpha hydrogens of aldehydes or ketones more acidic, and why? The alpha hydrogens of aldehydes are more acidic than ketones because the ketone, the extra alkyl group on the ketones shield, I guess they destabilize carbanions. How does steric hindrance affect the relative reactivity of aldehydes and ketones? Well, because in ketones there is greater steric hindrance, ketones are less reactive than aldehydes. All right. Pretty confident about those. 7.2, enolate chemistry. Due to the acidity of the alpha hydrogen, aldehydes and ketones exist in solution as a mixture of two isomers, the familiar keto form and the enol form. Keto-enol tautomerization. Enolate. The enol form gets its name from the presence of a carbon-carbon double bond. The En component and an alcohol, the Ol component. The two isomers, which differ in the placement of a proton and the double bond, are called tautomers. Let's write that down. Tautomers. The equilibrium between the tautomers lies far to the keto side, so there will be many more keto isomers in solution. The process of interconverting from the keto to the enol tautomer, shown in figure 7.2, is called enolization, or more generally, tautomerization. By extension, any aldehyde or ketone with a chiral alpha carbon will rapidly become a racemic mixture of the keto and enol forms as the keto and enol forms interconvert, phenomenon known as alpha racemization. All right. Let's write down that. Let's move this tautomers over. Let's write keto enol. The two forms are the two tautomers. We call this enolization, which is tautomerization. Enols are, we have this chart here of enolization or tautomerization. We have the keto form and the enol form. Should we write down that the keto form looks like the keto we know? Enol form has a OH, and the double bond has moved to one of the R groups. All right. Enols are important intermediates in many reactions of aldehydes and ketones. The enolate carbanion results from the deprotonation of the alpha carbon by a strong base as described earlier. Common strong bases include hydroxide ion, lithium disopropylamide, LDA, and potassium hydride, KH. Let's write down some of these. Strong bases. Strong bases include hydroxide ion, OH, lithium disopropylamide, LDA, and potassium hydride, KH. A 1,3-dicarbonyl is particularly acidic because there are 2 carbonyls to delocalize negative charge, and as such is often used to form enolate carbanions. Once formed, the nucleophilic carbanion reacts readily with electrophiles. We will see one example of this shortly in the Aldol Condensation. Another example of this type of reaction is a Michael addition. Michael addition is shown in figure 7.3, in which the carbanion attacks an alpha-beta unsaturated carbonyl compound, a molecule with a multiple bond between alpha and beta carbons next to a carbonyl. So A, the base deprotonates the alpha carbon, making a good nucleophile. B, the carbanion attacks the double bond. Resulting in a Michael addition. So this is another molecule comes over and attaches to that carbanion. This reaction proceeds as shown due to the resonance stabilization of the intermediates. The better you understand the resonance forms of molecules, the more you will be able to predict the specific location on a molecule where a reaction will occur. Let's write down this Michael addition. Do we need to write down Michael addition? No, we're going to leave it. All right, I don't know how important this Michael addition is, so I'm going to leave it for now. Kinetic and thermodynamic enolates. Given a ketone that has 2 different alkyl groups, each of which may have alpha hydrogens, 2 forms of the enolate can form, with the carbon-carbon double bond between the carbonyl carbon and either the more or less substituted carbon, as shown in figure 7.4. The equilibrium between these forms is dictated by the kinetic and thermodynamic control of the reaction. The kinetically controlled product is formed more rapidly but is less stable. This form has the double bond to the less substituted alpha carbon. As expected, this product is formed by the removal of the alpha hydrogen from the less substituted alpha carbon because it offers less steric hindrance. The thermodynamically controlled product is formed more slowly but is more stable and features the double bond being formed with the more substituted alpha carbon. Accordingly, this is formed by the removal of the alpha hydrogen from the more substituted alpha carbon. So let's draw this ring they have here. They have CH3 and we have two enolates, the thermodynamic product and the kinetic product. I guess since there's more steric hindrance on the one, I guess. Is that the one? Sorry, give me a second. All right. So yeah, this is the one carbon or carbonyl carbon is the one connected to oxygen. The 2 carbon is connected to a methyl group. So the one with the methyl group has more steric hindrance, so it's slower to form the thermodynamic product, but it's more stable. While the kinetic product forms easier because there's less steric hindrance on the 6 carbon over here. But while it's quicker to form, it is less stable. All right. Each of these two products is favored by different conditions. The kinetic product is favored in reactions that are rapid, irreversible, at lower temperatures, and with a strong sterically hindered base. If the reaction is reversible, the kinetic product can revert to the original reactant and react again to form the thermodynamic product. The thermodynamic product is favored with higher temperatures, slow, reversible reactions, and weaker, smaller bases. So let's write down that the kinetic product what did it say? It was slow. No, the kinetic product is fast. Kinetic product is favored in reactions that are rapid, irreversible, lower temp, strong hindered base. The thermodynamic product will happen at higher temp weak or small base. I guess, yeah, I guess a little counterintuitively, the kinetic product is the fast one, even though it happens at lower temperatures. So because it's a fast reaction, it can happen at lower temperatures. Slow. All right. Enamines. Just as enols are tautomers of carbonyls, enamines are tautomers of imines. Let's write that down. Enamines are tautomers of imines. An imine is a compound that contains a carbon-nitrogen double bond. The nitrogen in the imine may or may not be bonded to an alkyl group or other substituent. Through tautomerization, movement of a hydrogen and a double bond, imines can be converted into enamines as shown in figure 7.5. And in 7.5 on the right is the imine form, which is thermodynamically favored over the enamine form on the left. So let's draw these imines and enamines as well. We have N attached to something. I guess an NH. We have a carbon-carbon double bond. And then we have additional R groups. Sorry, give me a second. My nose really itches. I'll be back. All right. Sorry about that. We're back. We are looking at the tautomerization of imine into an enamine. We have our structure over here, and we have the enamine over here. Carbon, 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 carbon. All right. Got the enamine form over here. We got the imine on the right. All right. What are tautomers? They are slightly different configurations involving the loss of a hydrogen and the movement of a double bond. Movement of a hydrogen and a double bond. What tautomer of aldehydes and ketones is thermodynamically favored, keto or enol? The keto form is favored. What role does the enolate carbanion play in organic reactions? Nucleophile, electrophile, oxidizing agent, or reducing agent? What role does the enolate carbanion play? I guess it becomes a electrophile, or it becomes a nucleophile. It attacks an electrophile. It's like a lone pair, so it's like a base acting as a nucleophile. All right. What conditions favor the kinetic enolate form, the thermodynamic enolate form? The kinetic is lower temperatures or using a strong hindered base. The thermodynamic product is made in higher temperatures or using a weak or small base. Let's check the answers real quick. 2. Tautomers are isomers that can be interconverted by the movement of a hydrogen in a double bond. The keto form is thermodynamically favored. Number 3, enolate carbanions act as nucleophiles. And 4, because the kinetic enolate forms rapidly and can interconvert with the thermodynamic form, if given time, the kinetic form is favored by fast, irreversible reactions, such as with strong, sterically hindered base and lower temperatures. The thermodynamic form, on the other hand, is favored by slower, reversible reactions with weaker or smaller bases and higher temperatures. All right. Aldol condensation. The Aldol condensation is another vital reaction for the MCAT. This reaction follows the same general mechanism of nucleophilic addition to a carbonyl as previously described. In this case, however, an aldehyde or ketone acts both as an electrophile in its keto form and a nucleophile in its enolate form. And the end result is the formation of a carbon-carbon bond. As shown in figure 7.6, when acetaldehyde, ethanol, is treated with a catalytic amount of base, an enolate ion is produced. The enolate is more nucleophilic than the enol because it is negatively charged. We have a diagram of aldol condensation. Step 1 is forming the aldol. An enolate ion is formed, which then attacks the carbonyl carbon, forming an aldol. So let's draw out each of these steps. Start with an aldehyde. Whoops. All right. And we got some red arrows as well. So what is an aldol exactly? Is an aldehyde that turns into an alcohol. An enolate of an aldehyde under basic or acidic conditions So first we make an enolate, which then the enolate with the carbanion acts as a nucleophile and attacks another aldehyde molecule's carbanion, making this complex. Not carbanion, carbonyl carbon. It attacks the carbanion, attacks the carbonyl carbon. The double bond opens up, and then that oxygen with the negative charge attacks another hydrogen, becoming an alcohol. So we take a ketone, or we take an aldehyde and attach it to another aldehyde such that we end up with one aldehyde and one alcohol. That's our aldol. All right. This nucleophilic enolate ion can react with the electrophilic carbonyl group of another acetaldehyde molecule. The key to this reaction is that both species are in the same flask. The product is 3-hydroxybutanal, which is an example of an aldol, a molecule that contains both aldehyde and alcohol functional groups. Note that mechanism is still called an aldol reaction even when the reactants are ketones. With a strong base and high temperatures, dehydration occurs by an E1 or E2 mechanism. We kick off a water molecule and form a double bond, producing an alpha-beta saturated carbonyl, as shown in figure 7.7. So step 2 is dehydration. Dehydration, step 2. And let's draw our aldol. Without all the hydrogens. You know what, I'm going to put the H on there just like they have it. 1H, but not all of them. Yeah, I'm going to draw all the H's on there. We lose the OH on top. We lose H's from here. I guess so. This will have 1, 2, 3. This will have a hydrogen. This will have a hydrogen as well. So there will be an H here and an H here. They don't draw those in, so we won't either, but we also won't draw these in over here because they're implied, right? Well, I guess it changes from 2 to just 1 on each side. All right, fine. We'll draw them in. All right. Aldol condensations are most useful if we only use one type of aldehyde or ketone. You know what? I'm going to also label these alpha and beta. Aldol condensations are most useful if we only use one type of aldehyde or ketone. If there are multiple aldehydes or ketones, we cannot easily control which will act as the nucleophile and which will act as the electrophile, and a mixture of products will result. This can be prevented if one of the molecules has no alpha hydrogens because the alpha carbons are quaternary, like Benzaldehyde. This reaction is referred to as a condensation reaction because two molecules are joined with the loss of a small molecule. This type of reaction is also a dehydration reaction because the small molecule that is lost is water. This is a condensation reaction. It's also a dehydration reaction. The Retroaldol reaction. Retroaldol. The reverse of this reaction is called a retroaldol reaction. To push the reaction in a retroaldol direction, aqueous base is added and heat is applied. The retroaldol reaction is useful for breaking bonds between the alpha and beta carbons of a carbonyl, as shown in figure 7.8. This reaction is facilitated by the intermediate if the intermediate can be stabilized in the enolate form, just as in the forward reaction. So let's also write the retroaldol reaction. The bond between the alpha and beta carbons of a carbonyl is broken. Alpha, beta. So put an OH, O, R group, we have HO minus or H2O in the other direction, and we have O, R, H plus and we have some arrows. Got the 1, the 2, and the 3. And here we have the 1, 2, 3. All right. What species acts as the nucleophile in an aldol condensation? Well, the aldehyde that with the carbanion. So not the keto form, but the enol form. The enol form acts as the nucleophile. What species acts as the electrophile? That would be the keto form. What is a retroaldol reaction? What conditions favor retroaldol reactions? A retroaldol is the reverse of breaking up an aldol into a aldehyde and a ketone. An aldehyde and a ketone, just aldehydes, two aldehydes. The aldol condensation can be classified under many categories of reactions. List some of these reaction types and provide a short description of each. Well, it's a dehydration because the condensation, what it's losing is water. Condensation because it's losing a small molecule. Two molecules are joined with the loss of a molecule, rather. Also goes by the name Aldol Condensation. All right. Let's check those answers real quick. 7.3, the enolate carbanion attacks as the nucleophile. The keto form of the aldehyde or ketone acts as the electrophile. A retroaldol reaction is a reverse of an aldol reaction and can be favored by the addition of base and heat. Oh yeah, I forgot to say it's favored with base and heat. In this reaction, a bond between the alpha and beta carbons of a carbonyl is broken. Number 4, an aldol condensation is a condensation reaction in which two molecules are joined to form a single molecule with the loss of a small molecule. A dehydration reaction in which a molecule of water is lost. And a nucleophile-electrophile reaction in which a nucleophile pushes an electron pair to form a bond with an electrophile. So there you go, also a nucleophile-electrophile reaction. All right. Well, that's it for the chapter. We'll jump into the practice questions. All right. Number 1, what is the product of the reaction below? Well, this is a aldehyde because instead of two R groups, there is just a hydrogen here. So an aldehyde and an alcohol. I guess if you can make, I guess we're doing enolates, so we'll assume that you make an enolate and then that carb anion will attack will oxygen act as a nucleophile here? Or as an electrophile? Where is the electrophile? I don't think there is an electrophile. I think this has got to be the nucleophile. And this is the electrophile. It loses a hydrogen. So the final product will be O, and then all this stuff, and CH3 on the other side. The hydrogen gets kicked out. It's got to be 1C. 2, the reaction below is an example of, and we have aldehyde turning into its enolate. Oh, it's not, because it's got the oxygen gets hydrated. Oh yeah, and the bond moves away. So the reaction is an example of tautomerization. 2b. 3. Which of the following reactions would produce the compound below? So if it's 1, 2, 3, 1, 2, 3. So yeah, you'd make this with with aldehydes. In strong base, like OH, LDA, or KH. And the exact molecules would be CH3CHO. That doesn't sound right. Oh yeah, it does. CHO. CH3CHO would be this molecule, this part of it, plus CH3CH2, CH2CHO. So it's not this one. CH2, not that one. CH3CHO, no. CH3CH2CHO. But then does there need to be more after that? So the aldehyde will make an enolate, and then that double bond will attack another molecule. So I guess the aldehyde can have this extra R group on it. We'll put the R on the aldehyde. So instead of this molecule, CH3CHO, it'll be CH3CH2CHO. So it'll be D plus CH3CH2CHO. I think D looks like our best bet. Let's go with D. Number 4. Why does the equilibrium between keto and enol tautomers lie far to the keto side? Keto form is more thermodynamically stable. The enol form is lower energy. The enol form is more thermodynamically stable. Neither 2 or 3 is correct. Only 1, the keto form, is both more thermodynamically stable and has lower energy. So 4 will be just A. 5, the aldol condensation is an example of which reaction types? It's a dehydration and a nucleophilic addition. 1 and 3 only. 5 is going to be B. Which of the hydrogens in the following molecule is the most acidic? Is it a nucleophilic addition? It's a nucleophile electrophile reaction, they said. Is that nucleophilic addition? Yeah, it is. Sounds right. All right. Which of the hydrogens in the following molecule is the most acidic? I think this one's probably the most stabilized, right? Because there's resonance between the double bond being here and the double bond being here. If this one goes, there's also resonance. Oh no, this is the one with the resonance. It's got to be B. When reacted with ammonia at 200 degrees Celsius, which enolate of a carbonyl containing compound would predominate? NH3 is a weak base or strong base? NH3 is a weak base. Weak or small base, you get the thermodynamic product. Let's go with, I mean, it's kind of high temperature, 200 degrees Celsius, but it's not like above, well, it is above boiling point of water. Is 200 high? You never told us how high was high. We do know that ammonia is a weak base. Yeah, weak base, we go with thermodynamic, 7B. Which of the following compounds would be most reactive toward a nucleophile? So which makes a strong electrophile? Pentanal, pentanone, pentane. Most reactive, so this is not the carbanion, but the carbocation. So alkyl groups will help in this case. So 1, 2, 3, 4, pentanal. Double bonded to oxygen, so that's pentanal. 1, 2, 3, 4, 5. 3 pentone. So there's our ketone. Pentane, or 1, 2, 3, 4, 5, 6, 7, 8, 9. 2 nonone. Which would be most reactive to a nucleophile? So the best carbocation. Alkyl groups stabilize carbocations. So I imagine the most substitute, it's not the most, yeah, the most alkyl groups, I imagine, would make the best electrophile. On the other hand, this one is aldehyde. And didn't we learn that aldehydes are more, or ketones, yeah, aldehydes are more reactive than ketones? So, even though this has all the alkyl substitution, I think the aldehyde still wins at H. So let's go with pentanal, A. And let's move these over and save these next to this problem here. All right. On to number 9. Alpha hydrogens of a ketone are acidic due to, here's a ketone, carbonyl, alpha carbon, alpha hydrogens, are acidic due to resonance stabilization. I guess so. The enolate form. The electron withdrawing properties of the alkyl groups. No. The electronegative carbonyl oxygen. Yes. To alkyl. The electron withdrawing properties of alkyl groups do not help in the case of carbanions. So 2 is not true. Just 1 and 3. 1 and 3 only. B. Which of the following is considered a tautomer of the imine functional group? The tautomer of imine is the enamine, C. 11, when succinaldehyde is treated with lithium disopropylamide, LDA, well, let's take a look at what do we use LDA for again? LDA is a strong base. So when an aldehyde is treated with a strong base, I guess it'll strip the hydrogen away and it will become nucleophilic, right? Becomes more nucleophilic. And it also generates a carbanion. So 1 and 3 are both true. I think it's got to be 11 is C. On to number 12. Which of the following best describes the final product of an aldol condensation? A 1,3, yeah, not a 1,2, but a 1,3 dicarbonyl. Oh, I don't know about that. An alpha beta unsaturated carbonyl. Alpha beta. Oh, unsaturated meaning it doesn't have the hydrogens? Well, alpha beta sounds right. They always told us alpha beta. They didn't say beta alpha anywhere. Alpha beta. What's the difference between an alpha beta and a beta alpha? Dehydration, the result is an alpha beta unsaturated carbonyl. Alpha beta unsaturated carbonyl 12C. The 1,3-dicarbonyl was in the case of a different reaction. Is that the Michael addition? The enols are important intermediates in many reactions of aldehydes and ketones. The enolate carbon ion results from the deprotonation of the alpha carbon by a strong base, as described earlier. Common strong bases include hydroxide ion, lithium, disopropyl amide, LDA, and potassium hydride. A 1,3-dicarbonyl is particularly acidic because there are two carbonyls to delocalize negative charge. Once formed, the nucleophilic carbon ion reacts readily with electrophiles. We will see this in Aldol condensation. Another example is Michael addition, in which the carbon ion attacks an alpha-beta unsaturated carbonyl compound. So the alpha-beta unsaturated is created not in this reaction, the 1,3, but in Aldol condensation. Where is our dicarbonyl? Yeah, forget the dicarbonyl. After dehydration, you have an alpha-beta unsaturated. Alpha-beta unsaturated carbonyl. 12 is C. 13, when benzaldehyde is reacted with acetone, which will react as the nucleophile. Benzaldehyde. That is not benzaldehyde. this is benzaldehyde. Which will act as the nucleophile. Well, all this electron withdrawing over here resonance structures. Do we have any resonance structures? What else can happen in that ring? For example, if this turns into this, and there's a double bond here, these bonds don't move around, but they're just in conjugation. So I think that is likely to happen. So I'll say that benzaldehyde after addition of strong acid, which will act as the when benzaldehyde is reacted with acetone, which will act as the nucleophile. Benzaldehyde after reaction with a strong base, to strip off that hydrogen. Weak base or strong base. The more substituted, see, if I use a strong base, then we'll get the less substituted. To get the more substituted, no, but this one is still more reactive than this one, right? Yeah, benzaldehyde after reaction with strong base. (13B). (14) 3-hydroxybutanol can be formed by the reaction of. So what they're looking is 2, 3, 4, 3-hydroxybutanol. Yeah, it looks pretty good to me. This can be formed by the reaction of a ketone or could be made by just acetaldehyde. Ethanal. 1, 2. Yeah, ethanal. That's what we did in the alcohol condensation here. Acetaldehyde is ethanal, right? I think so. Let me double check. Ethanal. It's also acetaldehyde, right? So ethanal in base, then an acid. Methanal, butanal, ethanol, butanal, ethanal. 14's got to be B. One, two. No, but we want the H's going the other way. H. That's 14, of course. Let's take this, move this over here. Put a little equal there. And then finally, number 15, the catalytic production of dihydroxyacetone and glyceraldehyde 3-phosphate, 2-hydroxy-3-oxopropyl dihydrogen phosphate from fructose, 1,6-biphosphate, 2s-3s-4s-5r, 3,4-dihydroxy-5-phosphonooxymethyloxolin 2-ill-methoxyphosphonic acid is what type of reaction? So we have acetone and aldehyde. The production of acetone and aldehyde from fructose biphosphate, which they say is a phosphonic acid, is what type of reaction? Well, since you're making an aldehyde and an acetone, I think it's going to be the opposite of an aldol condensation, right? So it's probably a retroaldol reaction, right? Let's go with retroaldol reaction. Let's check our answers. We have 1 is D, not C. 1 more mole of aldehyde reacts with 1 mole of alcohol via a nucleophilic addition reaction to form a product called a hemiacetal. In a hemiacetal, an OH group, an OR group, a hydrogen atom, and an R group are attached to the same carbon atom. So they say that it's D. So it should turn into an alcohol. It doesn't stay an aldehyde. It's got to open up. Yeah, I guess it's got to open up, right? The carbonyl has got to open. So my bad, forgot to open the carbonyl. What you end up with is D, not C. 2 is B, 3 is D, 4 is A, 5 is B, 6 is B, 7 is B, 8 is A, 9 is B, 10 is C, 11 is C, 12 is C, 13 is D, not B. Because benzaldehyde lacks an alpha proton, it cannot be reacted with base to form a nucleophilic enolate carbanion. Therefore, acetone will act as our nucleophile, and both choices A and B can be eliminated. In order to perform this reaction, which is an aldol condensation, acetone will be reacted with a strong base, not a strong acid, in order to extract the alpha hydrogen and form the enolate anion, which will act as a nucleophile. So, benzaldehyde. Let me double check what benzaldehyde looks like. I think I drew that wrong. No, that's benzaldehyde. It's just, this is the carbonyl, this is the alpha. So there's a double bond, there's 4 bonds to this carbon. There's no hydrogen. There's no alpha hydrogen here. So this can't be the nucleophile, this will be the nucleophile. So, acetone in a strong base, D. Finally, 14 is B and 15 is B. Well, there you have it. That is aldehydes and ketones 2, enolates. Next time, we'll get into Chapter 8, carboxylic acids. Thanks for